So we've just observed that when we do this limit process to find the derivative, we're always going to, as long as we're dealing with a polynomial, right, or a power, this is why it's called a power rule. So if I have an x to a power, then I'm always going to have x plus h to that power, and I'm always going to expand it using Pascal's triangle, as long as I have x to a power, right? And then out of the process, the only thing that's going to survive is the second term. So what I need is a pattern that tells me when I'm expanding something like x plus h to the fifth power or x plus h to the any power, how would I know what that second term is and then just say that's going to be the limit because the x to the fifth is going to cancel out. All the ones with higher power of h than 1 are going to end up being 0 at the end, and only the one that is linear in h will actually be the derivative. So how can I know what that term is going to be? So here's another look at Pascal's triangle. So this time I've sort of laid out how Pascal's triangle is telling you what x plus h to various powers is. So, and I wanted to notice that, you know, in Pascal's triangle, we always start with 1, 1, 1. Okay, that's not just formal. It actually means something. It means x plus h to the 0 power is 1, because anything to the 0 power is 1. X plus h to the first power is 1x plus 1h. Notice, by the way, that when you learned the pattern a plus b squared equals a squared plus 2ab plus b squared, that was the second tier in Pascal's triangle. So that when you learned this was a special case of this whole thing that extends infinitely. All right? Now, what we really want to know is, what about that second term? What is the second term in every one of these expansions? All right, and oh, I just realized I have a h squared here, and this should just be h. All right, h to the 1. Yeah. All right, so these are all the terms that have h in them. So what do you notice as a pattern here? That second term is always going to be, so let's say this is n, right? Let's say I have x plus h to the nth power. Then I know it's going to be, all right, so the first term is always x to whatever power you have, x to whatever power you have. So our first term is going to be x to the n. So how do I know the second term? Well, if I look at every time, the power is equal to the coefficient. The power is equal to the coefficient. The power is equal to the coefficient. In fact, the pattern here just goes 0, 1, 2, 3, 4, 5, right? So the next term is going to be whatever that power is, so n, and then x to, so how am I going to say what the exponent, the power of x is? Well, when I'm expanding x plus h to the fifth, the power of x is 4. If I'm expanding x plus h to the fourth, the power of x is 3. If I'm expanding x plus h to the third, the power of x is 2. And when I say the power of x is 2, etc., I mean the power of x in the second term, which determines what the derivative is. So what's the pattern? 5, 4, 4, 3, 3, 2. It's n minus 1. All right? And then it's going to be plus a bunch of terms that are going to go away, and then ending in h to the n. So I can actually use this idea. All right, so these are all terms with degree of h that is greater than 1. All right, it's 2 or more. This term actually has an h in it. Okay, so now if I can say, let f of x equal x to the nth power. So now I'm not even going to say what the exponent is. What would f prime of x be? Well, f prime of x, we can start by saying it's the limit as h approaches 0 of f of x plus h minus f of x over h. And then we can say that the x plus h is, f of x plus h is going to be x plus h to the n. I guess I'll go ahead and write that, x plus h to the n minus x to the n over h. So that equals limit as h approaches 0. Okay, now the x plus h to the n, here's what it is. It's x to the n plus x to the n, x to the n minus 1 h plus a bunch of terms that have degree of h greater than 1 plus h to the n minus x to the n, and that's all over h. So I've left out all these terms. I haven't said what they are, because I don't care what they are. The only thing I care about them is that they are terms with a degree of h that is greater than 1. Not equal to 1, but greater than 1. All right, so then I know that the extendeds cancel out, so this equals limit as h approaches 0 of n x to the n minus 1 h plus my bunch of terms ending in h to the n, and that is all over h. Now, all of these terms have h in them, so I can reduce that. Limit as h approaches 0 of n x to the n minus 1. These h's crucially cancel out. And equally crucially, since all of these terms have degree of h that is greater than 1, when I reduce them, I'm going to have a bunch of terms ending in h to the n minus 1. And these are all going to be terms where the degree of h is greater than 0. So crucially, the degree of h is at least 1. All right? So then I can evaluate this limit by substitution because all of these terms that contain, no matter how many of them there are, as long as there's finitely many of them, no matter how many of them there are, they're all going to be 0. So this equals the limit as h approaches 0, or actually it's not a limit anymore. This equals n x to the n minus 1 plus, and I'll go ahead and say, just to belabor the point, plus a whole bunch of zeros. How many zeros? I could figure it's in terms of n, but it's not worth thinking about. N x to the n minus 1. All right, so this is a crucial conclusion, that the derivative of x to the n is equal to n x to the n minus 1. Now, also critically, where n is a natural number, I could say whole number. All right, n has to be a natural number because my argument depends on Pascal's triangle. And for example, Pascal's triangle I don't have x plus h to the 2.5 or x plus h to the 2.9998, okay? Not on Pascal's triangle. So this only works, this is a rule for derivatives that only works for x to the n where n is a natural number. So what, you say? You say, so what about that rule? Well, I will tell you in the next video that that is a big deal and why.